Section 1.5 talks about elementary matrices and a method for finding the inverse of A. Now this is something that we've been doing for a bit, but we want to put them in order. Elementary row operations. These are the elementary row operations of matrix A. You could multiply a row by non-zero constant. That's elementary. You could interchange two rows if you wish. You could add a constant times one row to another. Kind of like saying take row 1 times 3 plus row 2, put the result in row 2. So that's stuff that we know. I just wanted to point that out. Now, we have a couple of definitions we want to talk about. Definition 1 says matrices A and B are said to be row equivalent if either, and hence each other, if either can be obtained from the other by a sequence of elementary row operations. And the elementary row operations are right there. Also, a matrix E, and this one we're going to find. A matrix E is called an elementary matrix if it can be obtained from an identity matrix by performing a single elementary row operation, just one. So you take the identity, say we're talking about 2 by 2. You could, so we say E is called an elementary matrix if it can be obtained from this identity by applying on it just one row operation. Exactly one. Looking in the book at examples 1 and 2, it says determine whether the given matrix is elementary. So we're thinking, okay, can we just do one operation? And again, if you notice, this does look like the identity. So assume this is the identity matrix. What do you think you could do to this to get that? Well, wouldn't you say it is elementary? Yeah, it is. And multiply row here. We could write it this way. Radical 3 times row 2 and row 2. There you go. So a single operation, that's it. Just multiply by a number, that's 1. How about B? We say B is also an elementary matrix. So to get from this to what they have, all what I have to do is interchange row 1 with row 3. And since that's the only operation that we do, pretty much that's elementary. 3, if I take 1, 0, 0, 0, 1, 0, and 0, 0, 1. If I take 9 row 3, add it to row 2, put the result in row 2. Isn't that a single operation? Multiply them by 9 and just add it to the first row. So this is elementary. And if I get to the last one, well, here we have a problem. I would have here, I would have to switch row 1 with row 2, no, row 2 with row 3. But also I would have to multiply a row 1 by a negative, put it back in row 1. That's more than one operation, so this is not elementary. It has to be a single operation. What would be a single operation? Doing just one of those 3. Single elementary operation, I'm sorry. So, how about this problem right there? It's asking find a row operation and the corresponding elementary matrix that will restore the given elementary matrix to the identity. So you want this to become the identity. How would you do that? Well, for this to become become the identity, we would take 3 row 1, add it to row 2, put the result in row 2. That will do the trick. Here, so let me see. If we take 1, 0, 0, 1, so if we take 1, 0, 0, 1, and if you multiply row 1 by 3 and add it to row 2, that will become 3, 1. There. So when they say find the row operations and the corresponding elementary matrix, there's the corresponding elementary matrix. And I'll tell you what we're going to do with that. There's a theorem of how to use those elementary matrices to do something else. For now, let's just find it. Here, I am given 1, 0, 0, 0, 1, 0, 0, 0, 1. So what would you do to that? What would you do to this to get that? Well, here we would take row 3 divided by 3, put the result in row 3. So we take the first we leave alone, the second we leave alone, and the third we divide by 3. And that's really how this is going to work. So every time you do one of these, do it on the identity matrix. Well, here we have the identity to be, now normally I try not to have you work on big matrices, but I wanted to get used to the identity matrix, and hopefully you don't mess that part up. Now what do we do here? We want this to become that. Well, I could see if I could take row 1 and switch it with row 3. Isn't that the only, no, I'm sorry, that's row 4, not 3, right? So what would that do to my matrix? And we call that E. That will make this 0, 0, 0, 1, the second you leave alone, the third you leave alone, and 1, 0, and if you're thinking again, why are we writing those? I'm going to show you. There's a theorem that says you could get the same result by multiplying E times something else. Whoa. And there it is. And on the last one, let's see how that works. If I take the identity, oh, let me just leave some space. If I take the identity matrix, I notice the only thing in there that's a negative 1 over 7. If I multiply this by a negative 1 over 7 and add it to the first row, take negative 1 over 7, row 3, and add it to row 1. So let's see how this works. That means I had 1, 0. Okay, so this is 0, 0, 0, 1. This is 0, 0, 1, 0. This is 0, 1, 0, 0. And if you multiply that by, let me see, multiply that by 1 over 7. My mistake. So that'll be E right there. So that's pretty much all you have to do. Pretty much whatever you do the operation, you do it on the identity matrix, and keep that as E for now. And let's see how that plays right there. Now, they're taking this in steps, and that's fine because if you put it all together, it's kind of confusing. Now, let's see where this is going to go. Observe. If I was looking at the identity matrix, do you see what we did? We must have multiplied row 1 by a negative 6. Isn't that what it is? If you multiply row 1 by a negative 6, you'll get that. Notice what happened if you take EA. If you multiply those two, this is 2 by 2. This is 2 by 4. The outcome is 2 by 4. I have all the space. Let me make those bigger. So what do we get? Let's see. To generate the first row, we use the first row. Multiply accordingly. And I'm not going to keep on doing that, but for now, so again, 6 plus 0 is a 6. 12 plus 0 is a 12. Negative 30 plus 0 is negative 30, and 6 plus 0 is a 6. For the bottom row, you notice that when you multiply those, 0 times the first is going to always be a 0, and just going to add the bottom, you end up at the bottom. So 0 plus 3, 0 minus 6, 0 minus 6, and 0 minus 6. And do you see that? All what we did to this was we took row 1 and multiply it by a negative 6, put it back in row 1. And notice what happened when you multiply the two matrices. If I was to multiply this top row by a negative 6, wouldn't that be the results? And as you see, a single operation or a matrix operation perform the same outcome. And of course, multiplying row 1 by a 6 is a lot easier than multiplying those two. If I looked at this one, look how messy that looks. Now, if I look here and I'm trying to figure out what did you do to the identity matrix to get a negative 4 there, you must have taken negative 4 row 1 and you added that to row 2. Put the result in row 2. That's what you must have did. Well, if that's the case, then guess what? If I multiply row 1 by a negative 4 and add it to row 2, they're saying if you multiply those, if you take EA, E is 3 by 3, 3 by 5. So the outcome is 3 by 5. So to generate the first row, I use the first row. To generate the second row, I use the second row, and to generate the third row, I use the third row, and accordingly multiply in order by this to get the first. And let's see, since that's 1 0 0, you're just going to get 0 2 on the first. You see that? And on the second, it's going to be negative 1, and those are going to be 0 0. So pretty much you're going to get the first row only. On the second row, do you see that you're going to get negative 4 times 2 plus 1 times 1, and the bottom's not going to count because that's 0. So that's negative 8 plus 1, which is negative 7. And for this, it's going to be negative 4 times negative 1, 4. Minus 3 is a 1. And then 0 minus 1 is a negative 1. And 16 plus 5 is 21. And 16, for the last 16 plus 3 is 19. And for the third row, when you multiply by 0 0 by 0 0 1, multiply the first by a 0, that's a 0, the second by a 0, that's 0. That's going to happen in all of those. The only thing that's going to remain would be the bottom row. Where's that race? Oh, here it is. Okay, I cluttered this. I just want to come on here, clean it up. There it is. All right, and again, if you really think about it, multiplying those two matrices is the equivalent of me multiplying. So this is what I did to the elementary. Well, do that for this and you get the same result. Multiply this by a negative 4 and add it to the second row. It should give you that row as well. Negative 8 plus 1, 4 minus 3, 0 minus 1, 16 plus 5, and 16 plus 3. So just making sure that you see that. And again, we need this for theoretical purposes, but for now, let's look at this. Do you notice here what you did? All what you did to the identity matrix, you took row 2, multiplied by 5, put the result in row 2. Now, they want to show that, look, EA gives the same results. If you take an elementary matrix and multiply it by A, it has the same outcome as you applying that operation on A. If I was to multiply a row 2 by 5 and put it back in there, wouldn't that be a 10 and 25? And they're saying, look, multiply 3 by 3, 3 by 2. The outcome is a 3 by 2. And to generate the first row, I use the first row. To generate the second row, oops, it didn't register. I use the second, and to generate the third, I use the third, multiply accordingly. Well, here 1, 0, 0 multiplied by those. 1 times 1 is 1 plus 0 plus 0, and 4 plus 0 plus 0. When I get to the second, 0 times 1 is 0. 5 times 2 is 10 plus 0. And when I get to this, 0 times 4 is 0. 5 times 5 is 25. When I get to the last, 0 times 1, 0 times 2, that's a 3, and that's a 6. And do you see, it's as if multiplying those two matrices is the same operation and me just multiplying that by a 5. And this is something we're going to come back to later on and use whenever the time comes. So it's much easier if you could find such row operations to just multiply the single matrix by that operation. I apply the single matrix, apply the operation on the single matrix instead of multiplying two matrices. Now here, they say, look, here they're saying, hey, tell me what E is so that when I multiply B, I get that matrix. Well, that's the same thing as looking at those. Say, look, the first is the same, the last is the same. What did they do from this to this? Didn't they multiply row 2 by -3? So if I take the identity matrix, multiply row 2 by a -3, wouldn't that be it? So this homework, not a whole bunch of work, at least not in the first problems, but very important for what's coming. We want to make sure we get these elementary matrices out of the way. If you multiply E and there's D to get B, and here we took E times B to get D. Well, again, look at this. That's the same. That's the same. What did they do here? They had a -6. So wouldn't that mean they divided by a -3, except we don't divide? Well, you could divide. We take row 2 divided by -3, put the result in row 2. Well, that's 1, 0, 0, that's 0, 0, 1. The middle will be 0. If you divide it by -1/3, it would look like that. And again, we have a use for those. Just bear with it and you'll get how this works. All right. Now, the next set of matrices, again, I really want you to get the hang of this really quick and get used to this forward and backwards, and that's what we're doing now. Again, tell me what is E, so that you take E times B and you set it equal to F. And again, I copied those for you. Well, look, that's the same. And I don't want you to think over always doing something for the second row. That's not true. To the second row, yeah. So let's see how this works. Well, I went from 6 to 8. How would I do that? I went from -6 to 8. No, -6 to 8. Remember, this is elementary. You must have did one thing. So either you could switch rows, that's allowed, or you could interchange rows, that's allowed. You could multiply a row by a non-constant, or you could multiply a row by a number and add it to the second row. That falls under the elementary row operations, and that's how you get the elementary matrix. So if I'm looking at this, here, I can't multiply, like for example, this is 1, this is 21. You can't say I divided by 21 because -6 divided by 21 is not 8. So here it looks like they multiplied a row by a quantity and added to the second row. Well, let's see what they did. I thought they would add row 1, but that's not working. Why is that? We multiply, so if you take this, to get an 8, oh boy. Okay, B, let me make sure. B, B, E, B equal F, B and F, B and F. B is, oh, okay. Caught it. Let me fix that. Made a mistake. Hold on. Okay, I fixed the problem. I actually had D instead of B. I'm like, wait, that's not working. So in this case, they're saying this is elementary. Again, you can't always find an elementary operation, otherwise life would have been easy. So if I take, what did I do? Now let's see. I did something to this matrix, so to get an 8 right there. Well, to get an 8 right there, I could have multiplied this by 2 and added to that. Would that work on this 8 and 2? Yep, there you go. So I must have did twice row 2, twice row 3, plus row 2 in row 2. Well, what does that mean? If I'm looking at 1, 0, 0, 0, 1, 0, 0, 0, 1, if I multiply row 3 by 2 and add it to row 2, wouldn't that become 1, 2, 0, 0, 1? And there it is. That's E. Similarly, if I take, okay, let me write that where you can see it, 2 and 2. If I want to look at the last row, oh, you know what, let's leave it there, that's okay. Look at the last and figure out what would be the elementary matrix that you multiply F with to get B again. Well, let's see. Again, they left the first and the last. It seems all the work is done right there. So how do you get that? How do you get an 8? Well, I could say, okay, there are many operations. Remember, you're only allowed one operation and that's it. Now, oh, what do you do to this? If I multiply this by a -2, that would be -6. -8 plus 1 is -7, and -2 plus, okay, there it is. So if you take -2 row 2, row 3, add it to row 2, put the result in row 2. Now, 1, 0, 0, 0, 1, 0, 0, 0, 1. If I multiply by a -2 and add it to that, the only thing that will change is that. And we already showed in the first example that if you multiply those two matrices, it's the same as doing this operation to that matrix. Now, recall from the previous section how to find an inverse. Now, there was something I didn't talk much about because there was no point then, but this is what it says. To find an inverse, you take 1 over the determinant. Now, you're dividing by this determinant. What happened if the determinant equals 0? This will be undefined. So, notice what they say. The matrix is invertible if and only if this denominator does not equal to 0. And if it equal to 0, so if it doesn't, if and only if it doesn't equal to 0, it is invertible, and it's invertible, it doesn't equal to 0. If it equal to 0, this is not invertible. You can't find an inverse. Recall? So they say, okay, find a inverse if it exists. Well, let's see. First things first. The product of those, is that a 0? That's -16 minus 15. No, it's not. So the inverse of this will be 1 over the determinant, 1 over -16 plus 50 minus a -15. Swap the diagonals and multiply the non-diagonals by a negative. That's a -1. So the inverse to this matrix is simply 16, -5, 3, and a 1. And let's do it again on part B. If I cross those, that will be a -12 minus a -12. So the determinant of A is -12 minus a -12, which is 0. So this is not invertible. And that means an inverse to that does not exist, and therefore I cannot come up with it. Now remember, this trick only works on a 2 by 2. I just wanted to show what happened. Remember, there was another way of finding an inverse. If you want to find the inverse of A, you make a line right there and you put the identity matrix on the left. Do row operations, and when you get the identity on the left, the inverse will be on the right. Well, let me just show you. I just want to make sure you see what happens, because this only works on a 2 by 2. When you deal with a 3 by 3, a 4 by 4, now the reason we didn't do that on those two problems, because it's a lot quicker to use the formula. If I am to do raw operations, my first goal will be to make that a 0. So I want this to be reduced raw echelon form. I'll take twice row 2 plus row 1, put the result in row 2. Again, the goal is to make that number down there is 0. If I multiply this by and 2, that becomes negative 6, negative 4, 0, and a 2. And if I add it to the first row, and I'm going to put the result in the first row, in the second row, I'm sorry, because I want that to be a 0. I'll get a 0, 0, a 1, and a 2. Well, what do you notice? Do you see that that's 0, 0? There's no way of getting the identity anymore. For this to work, I need the left to be 1, 0, 0, 1. If that happens, whatever's on the right-hand side, those 2 by 2, that will be the inverse. Anytime you cannot find an inverse does not exist, and we'll talk about what that means as far as solutions pretty soon. That will happen. One of the rows zero out in the original, which means there's no way of getting the inverse, and therefore you cannot just find the inverse. So every elementary, remember what elementary is? Every elementary matrix is invertible, and its inverse is also an elementary matrix. So here's one. Again, let's see what they want. Use the inversion algorithm to find the inverse of the matrix if they exist. Now, this process is really tedious and long, and the chances of making an error is very high. So just work with it. Work slowly as you're doing this. So there is no shortcut to this. This is the only method we have so far. My goal is to make the left this exactly like this matrix, which is the identity. So I start with the same thing what we did before. I want to make that a 0 and that a 0. How do you do that? So you take negative row 1 plus row 2, put the result in row 2. Take negative row 1 plus row 3, put the result in row 3. And what did we get? The remaining outcome would be what? Row 1 I'm using, but I'm not changing. Now, if you read the book, they might multiply row 1 by a 5 first. You could do that if you wish. If I multiply this by a negative, that becomes negative 1/5. Since I'm doing the same, that's 0. Negative 1/5 plus 1/5, that's a 0. Negative 1/5 minus 4/5, that's negative 5 over 5. If I multiply this by negative 1, that becomes 2/5. If I take 2 over 5 and add it to 1 over 10, well, that is 4 over 5 plus 1, 4 over 10 plus 1 over 10 is 5 over 10. 5 over 10 is a half, and that's the same. Now, if I multiply this by negative 1 and add it to this row, that will become negative 1, 1, 0. If I multiply this by a negative 1 and add it to this row, that will become negative 1, 0, 1. I just want to make sure you see it. I'm going to do that one. So if I multiply row 1 by a negative 1, that's negative 1/5, negative 1/5, 2/5, negative 1, 0, 0. And if I add that to row 2, that zeroes out, that zeroes out. That's 3 over 5. I'm sorry, times 2 times 2, that's 4. 5 over 10, which is a half. That's a negative 1, that's a 1, and that's a 0, and that's what I wrote there. So you could put it on the side, write it out if you want. That's not an issue. Actually, I might do that for the next step. Now, the next step, I want to make that a 0. Well, there's a problem. If I use row 1, that will change this 0. So the only way to really make that look like the identity is to swap the rows. Take row 2 and swap it with row 3. But remember now, it's going to apply to the entire row. Row 1, if I switch those two rows, that will be 0, -1, 1/2, -1, 0, 1. And this row will become the last 0, 0, 1/2, -1, 0. Okay, now the goal was to make those 3 zeros. I did. Now, the reverse steps, 2 more steps. First step, I'm going to make those 2 zeros, and then I'll make the last one 0 right there. And I'm done. Well, I don't know why I wrote that so small. I'm going to rewrite it a bit bigger. Give me a sec. Now, again, I could multiply this by -1/2 and add it to that and proceed. I have a suggestion. This is only me, though. You don't have to do this if you don't want to. I strongly suggest from the beginning, before I even started, I would have multiplied this by 5, this by 5, and this by 5. So here, I would say, you know what? I'll take an extra step. Take row 1, multiply it by 5, put it back in row 1. Take row 2, multiply it by 2, put it back in row 2. And take row 3 multiplied by 2, put it back in row 3. I would rather deal with integers than deal with fractions. This is 1, 1, -2, 5, 0, 0. This is 0, 0, 1, -2, 2, 0. And this is 0, -2, 1. I forgot that I switched them. We switched row 1 with row 2. Crap. Oh boy. If we switch them, then that will become 0, -1. Again, when I erased it, I just copied the old. I copied that pretty much, which is a mistake. 0 go. Much better. Okay, so if we do that, then that will become multiplied by a 2, multiplied by a 2. Okay, now it's much easier to play with. Again, you don't have to, but I prefer that. I'm going to take negative row 1 and negative row 3, add it to row 2, put the result in row 2, and I'm going to take twice row 3 plus row 1, put the result in row 1. So I'm looking at if I multiply this by a -1 and add it to the second row, 0 plus 0 is 0. 0 minus 2 is -2. -1 plus 1 is a 0. 2 plus a -2 is a 0. -2 plus 0 is a -2. And 0 plus 2 is a 2. If I multiply row 3 by a 2, then that row becomes 0, 0, 2, -4, 4, and a 0. And if I add it to row 1, I'll get a 1, 1, 0, 1, 4, and a 0. So as you see, 3 by 3 will take 4 steps pretty much. 5, because at the end you're going to have to reduce each one and make it a 1. Last step is to make that a 0. And to do that, I would say take I meant this. And you should use that row. So the last step, I would say take row 2. Okay. So take row 1, multiply it by 2, add it to row 2, put the result in row 1. this is set. I'm not going to use it. This one I have to modify in a minute. The only thing that's going to change is row 1. If I multiply row 1 by 2, I'll get 2, 2, 0, 2, 8, 0. Add it to row 2. I'll get 2, 0, 0, 2, 6, and a 2. Now, hopefully I didn't make a mistake. Like I said, the chances of making a mistake is very high. And if I do now the last step, take row 1 divided by 2, put it back in row 1, and take row 2 divided by negative, or multiply by negative 1/2 to be politically correct. And the outcome would be 1, 0, 0. And if I divide that by 2, that's 1, 3, 1. 0, 1, 0, divide by a negative 2, 0, 1, negative 1. And the last one is okay. And guess what? That's the inverse, provided we made no mistakes. Again, the chances of making a mistake is pretty high. You should work very slowly, but that's pretty much how you run these. Now, I do have the answer. Okay, perfect. I got the right answer. Here's another one. Now, again, before I start, before you do any modifications, you have to write, and this is the only way we could find the inverse up till now, right? It's not a 2 by 2, so we can't find a shortcut. Well, if it was you, I would say, look, before I start, take row 1 times 5, put it back in row 1, take row 2 times 5, put it back in row 2, and take row 3 times 5, put it back in row 3. And what will happen? I'll get a 1, 1, negative 2, 5, 0, 0. I'll get a 2, negative 3, 0, 5, 0. And a 1, negative 4, 1, 0, 0, 5. And now I'll proceed just like we did. I want to make those two 0 first. So the way that would happen, I will take negative twice row 1 plus row 2 in row 2, and I'll take negative row 1 plus row 3 in row 3. So row 1 I am using, but I'm not changing. If I multiply row 1 by negative 2, that's a negative 2, negative 2, 4, negative 10, 0, 0. Add that to row 2, 2, negative 3, 0, 5, 0. I'll get a 0, negative 5, 1, negative 10, 5, and a 0. Okay, and if I multiply row 1 by a negative, I'm looking at negative 1, negative 1, negative 2, negative 5, 0, 0. Add that to the third row. I'll get a 0, negative 5, negative 1, negative 5, 0, 5. Let me make sure of the numbers. Crap, I see the mistake. Let me fix it. The mistake was that's a 10. You want to multiply this by a 10. Because again, I have the answer to those, and it wasn't working like it is right now. So let me fix that really quick. That shouldn't take long. And let's see. If I multiply by a 10, that will be a 4, negative 6, negative 3, 0, 10, 0. Multiply this by a 10, that's a 2, negative 8, 1, 0, 0, 10. Okay, now that'll change a few things. If I actually, now if I take negative 4 row 1 plus row 2 in row 2, and if I take negative 2 row 1 plus row 3 in row 3. I don't know why I'm writing so small. I have all the space on the planet. Take negative 4 row 1 plus row 2 in row 2, and take -2 row 1 plus row 3 in row 3. Well, let's see. Multiply this by a -4. -4 plus 4, that's a 0. Negative, that's -10. That's 8. 8 minus 3 is 5. -20 is 10 and 0. And if I multiply by a -2, -2 plus 2 is 0. -2, that's -10. -2, that's 4, that's 5. -10, a 0 and a 10. Oh, and obviously, if I take negative row 2 plus row 3 in row 3, what would happen? If I add those two, wouldn't that become 0, 0, 0 with a minus, of course? That become positive 10 minus 10, -5 plus 5. It doesn't matter what that is. Once this zeroes out, we say this is not possible. This is not invertible. Again, a lot of work to get there. Okay, and here I'm not going to work this out all the way. This is easy to play, but this one. But I just wanted to point out that what you could do, you could, before you start, again, make sure you put those as zeros. So you could say, you know what, take row 1 divided by radical 2, put it back in row 1, and take row 2 divided by radical 2, put it back in row 2. And what would happen, you're looking at now 1, 3, 0, but this will be 1 over radical 2, 0, 0. And this would be a -4, 1, 0, 0, 1 over radical 2, 0, and this remains the same. The work here is not intense. First step, multiply row 1 by 4 added to row 2, that will become a 0. And then all what you have to do is, you know what, let's do it, minus well. So if I take -4 row 1 plus row 2 in row 2, 1, 3, 0, 1 over radical 2, 0, 0, multiply by a 4, that's -4, -12, and that is 0, -4 over radical 2, 0, 0. If I add those two, that's a 0, that's a -11, that's a 0, that's -4 over radical 2, 1 over radical 2, 0, and this remains the same. And now, if I could make that a 0, I'm set. How do you do that? If you multiply row 2 by 3, row 1 by 11, and put the result in row 1, and that should do the trick. And if I look at 3 times row 2, 3 times row 2 will be 0, 3, yeah, -33, 0, -12 over radical 2, 3 over radical 2, and a 0. And if I multiply 11 times row 1, that's 11, that's 33, that's 0, that's 11 over radical 2, that's 0 and a 0. And if you add those, you get 11, you get 0, you get 0. 11 over radical 2 minus 12 over radical 2 is -1 over radical 2, 3 over radical 2, and a 0. The numbers are not pleasant, they're kind of annoying, but you get the idea. Now all what you have to do, take row 1 divided by 11, put it back in row 1, take row 2 divided by -11, put it back in row 2, and basically you're done. So you end up with 1, 0, 0. If you multiply by 1 over 11, you get negative 1 over 11 radical 2, 3 over 11 radical 2, and a 0. Divide by a negative 11, that will be 4 over 11 radical 2 and negative 1 over 11 radical 2. Hopefully I didn't make a mistake, but you get the idea of how that works, and this is the inverse of A. Now, we'll do the same here. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Again, I'm not really a big fan of doing a 4x4, but some of those are really easy to do. I want to make sure that you believe that as well. I want to make all of these 0. Well, step 1, take negative row 1, add it to row 2 in row 2. Take negative row 1, add it to row 3 in row 3. And take negative row 1, add it to row 4 in row 4. What that does, so 1, 0, 0, 0, 1, 0, 0, 0. If you multiply row 1 by a negative, it's the same one. Add it to the second row, 0, 3, 0, 0, negative 1, 1, 0, 0. If you add it to this row, that's 0, 3, 5, 0, negative 1, 0, 1, 0. And if you add it to the last, that will be 0, 3, 5, 7, negative 1, 0, 0, 1. Now, second step, make those two 0. Take negative row 2 plus row 3 in row 3, and take negative row 2 plus row 4 in row 4. And what that does, multiply this by a negative 3. Well, what's going to happen? By a negative 1, I mean. That's going to be 0. Negative 3 plus 3 is 0. The 5 remains. Now, negative 1 plus 1 is 0. Negative 1 plus 0 is negative 1, 1, 0. And if you take negative row 2 and add it to row 4, that's 0, 0, 0, 7. Those will give you a 0. That will give you a 1, a 0, and a 1. And as you see, all what I have to do now is take row 1, oh, no, row 2 divided by 3, put it back in row 3. Row 4, oh boy. Row 2 divided by 3, put it back in row 2. Row 3 divided by 5, put it back in row 3, and row 4 divided by 7, put it back in row 4. So what will happen? And this will be my inverse, provided we didn't make any mistakes on any of those. That's pretty much it. All right, now we're almost done. And this is the only section we're going to do today. I'd like to look at number 20. I would have done it says find the inverse for each 4x4 where k1 through k sub 4 are not 0. All of them are non-zero. Because if one of them is 0, you can no longer do it. Well, aren't you going to first take row 1 and switch that with row 4, and take row 2 and switch it with row 3. If that's the first step, then I'm going to get K4, K sub 4, 0, 0, 0, 0, 0, 0, 1. And if I put the first one last, it looks like this. And if I switch those two, then I'm looking at 0, K3, 0, 0, 0, 0, 1, 0. And I'm looking at 0, 0, K sub 2, 0, 0, 1, 0, 0. All what I have to do right now is take row 1, multiply it by 1 over 4, put it in row 1. Take row 2, multiply it by 1 over K sub 3, put it in row 2. Take row 3, multiply it by K sub 2, put it back in row 3. And take row sub 4, multiply it by 1 over K1 or divide it by K1, put it back in row sub 4. Now I know that these are going to become all ones, so the identity matrix will automatically be 0, 0, 0, 1 over K sub 4, 0, 0, 1 over K sub 3, 0, 0, 1 over K sub 2, 0, 0, and 1 over K sub 1, 0, 0, 0. All right. And the last example we have would be the following. Now, the goal is to make, again, the identity. You should write the identity first, and then you begin. Oops, messed up. So, if I want to make that a 0, I would take row 1, multiply or divide it by k, and add it to row 2, put the result in row 2. That's my first step. 1 at k, 0, 0, 0, 1, 0, 0, 0. So if I multiply row 1 by 1 over k, that becomes 1, oh, negative 1 over k. That becomes negative 1, 0, 0, 0, negative 1 over k, 0, 0, 0. If I add it to 1, k, 0, 0, 0, 1, 0, 0, what would happen? I'll get a 0. I'll get a k, 0, 0, negative 1 over k, 1, 0, 0. And now, as you guess, we're going to do the same. Now I'm going to go to the second row, say, hey, let's make that a 0. How do you do that? Well, obviously, you take negative row sub 2 divided by k, not that color, plus row sub 3, put the result in row sub 3. So row sub 1 is k, 0, 0, 0, 1, 0, 0. Now, of course, you could divide row 1 by k right now and put it back in row 1. That'll save you time on the long run. So you make that basically 1, and that's 1 over k. Now, row 2, if I take row 2, multiply it by negative 1 over k, it becomes 0, negative 1, 0, 0, 1 over k squared, 1 over k, negative 0, 0. And if I add that to row 3, I'm not lining those up properly. So I have 0, negative 1, 0, 0, 1 over k squared, negative 1 over k, 0, 0. And if I add to that 0, 1, k, 0, 0, 0, 1, 0, I'll get 0, 0, K0. So if I divided that, that's 1, 0, 0, 0, 1 over K 0, 0, 0. Now, I lost track. All right, 0, K 0, 0, negative 1 over K 1, 0, 0. So if I multiply row 2 by negative 1 over K and add it to row 3, put the result in row 3. This is the product by 1 over K of this. Negative, 0, negative, okay, good. And if I add it to this, I'll get 0, 0, K, 0, 1 over K squared, and negative 1 over K, 1 and a 0. Okay. And also, as I proceed, a bit longer than I anticipated, but it's okay. Okay. Now I would move to that top and say, okay, now let's look at what happens. If I take 1 over K times, oh, that's not working. Okay. If I take 1 over K times row 3 plus row 4 negative, put the result in row 4, I'll notice that I'm looking at 1, 0, 0, 0. And I could, I'll do that at the end instead of keep on adding to the list. So if I multiply this by negative 1 over K, 0, 0, negative 1, 0, negative 1 over K cubed, 1 over K squared, 1 over K and a 0, and if I add that to 0, 0, 1 K, 0, 0, 0, 1. I'll get 0, 0, 0 K, negative 1 over K cubed, 1 over K squared, 1 over K, and a 1. Cubed squared, 1 and a K. So negative 1 over K cubed, 1 over K squared, 1 over K, and a 1. Now, take row 2 divided by K, put it back in row 2. Take row 3 divided by K, put it back in row 3. And take row 4 divided by K, put it back in row 4. That will make all of these be in 1 across the diagonals, which is the identity. And the inverse will simply be row 1 is 1 over K, 0, 0, 0. If I multiply by 1 over K, I'll get negative 1 over K squared, 1 over K, 0, 0. Multiply by 1 over K, I'll get 1 over K cubed, negative 1 over K squared, 1 over K and a 0. And the last one, I'll get negative 1 over K to the 4th, 1 over K cubed, 1 over K squared, and 1 over K. And that would be my identity matrix. I know it doesn't look pretty. Again, we normally don't do a 4x4. I normally don't do any of those, but these are the only ones I could find with the K. Now, summing everything up, last aspect we have to do. if the elementary matrix E results from performing a certain row operation, kind of like what we did, one operation on each, and if A is an n by n matrix, so it's not a square matrix, then the product EA, like we did, is the matrix result when this same row operation is performed. I already mentioned that and showed that. Instead of multiplying, you could just do to that, to the operation, and there it is. Express the matrix and its inverse as a product of elementary matrices. All right, this one we have to be patient for, so let's look at that and work at it slowly. The goal is to make this the identity matrix. The first thing I do, I would take, normally, let's say I want to make that a 0. So I'll take 5 times row 1 plus row 2 and row 2. So here we will say the first elementary operations we did. So again, if I had 1, 0, 0, 1, if I was to multiply row 1 by 5 and add it to row 2, wouldn't that be it? Oops. Wouldn't that be it right there? So that's the first operation that we did. And what happens, that will make this now 1, 0, 0, 2. Then what would I do? After that, I want to make that a 1. Wouldn't you say take row 2 divided by 5? Oh my God. Take row 2 divided by 2, put it in row 2. Well, the same deal. Look at this. The second operation will be what? The second operation on the identity matrix. If I take row 2 divided by 2 and put it back in, wouldn't that be what it looks like? You know what? I should have left the first one. Let me write it down. So the first operation was take first operation was take negative 5 row 1 plus row 2 and row 2, and that will yield this, and there's E2, and that should be it, because if you do the actual division, you will get a 1, 0, 0, 1. Well, basically we're done, but this is what we concluded. This is the work now. If I take those and I now, I could say this matrix A, I could take this matrix A. We applied E1 first to it. Then we applied E2 in that order. If I do that, I'll get the identity. So we applied E1 first and then E2. I get the identity. But I could also say, hey, I love this part. I could say, but if I multiply by E2, E1 inverse, this will be the identity. So basically the left will be the A. Now, do you remember how this works? Wouldn't those switch order? Right there. If you take AB, the inverse of product of two matrices A and B, that becomes B inverse A, if you recall. And I could say that A, which is this matrix, right? The initial matrix is actually E1 inverse, E2 inverse, because when you multiply by the identity any matrix, you get the matrix back. And what are those? Now, those are very special because they are elementary operations. So the determinant of this is 1 minus 0, which is 1. So basically, you only swap the diagonals and multiply the non-diagonals by a negative. And here, 1 over the determinant, well, the determinant is 1/2. 1 over the determinant is 2. You're going to multiply by 2, swap those. So the 1/2 will be up there and the 1 will be here times 2. That's 1, 2, and those are 0. And did I do this right? E1, E2. Not only that, I could say the inverse. Well, what's the inverse? If I take the inverse of this, that will be the inverse of those. So those will be E2, E1 again. If I take A equal E sub 1 inverse, E sub 2 inverse. If I take the inverse of those, A inverse will be, remember, those will swap and the inverse will undo each other. And E2 is simply 1, 0, 0, 1/2 and 1, 5, 0, 1. And if you're not sure, you could multiply those and figure out whether this works or not. So here, if you multiply, you'll get 1 plus 0, that's 1, 0 plus 0, that's 0, negative 1/5 plus 0, and 0 plus 2. And that's really what we want out of it. We're going to come back to this and do it again. This is an equivalent. So this is a theorem that we always get. We're going to use that later on. We're not going to use it for a proof, but we're going to use the conclusion of it. And it's very crucial. Every section, they're going to compile and add to this. Eventually, we're going to get an equivalent statements of about 12 of those, which says if you have an m by m matrix, which is a square matrix, then the statements are equivalent. All of these are the same. Either they're all true or they're all false. One of the two. If you say A is invertible, then you're saying AX equals 0 has a trivial solution. Guaranteed. Then, the reduced raw echelon of form of A is the identity matrix. And A is expressed as the product of elementary matrices. That was the very last problem that I did. Your homework is not as long as the problems I did. It turned out all the even problems are long and complex. All the odd are more straightforward. So there's the homework, and that concludes this section.